Is my slide visible to all of you? Is my slide visible to all of you?
Yes, sir. It is visible.
Yeah. So let's start the discussion. So welcome you all to this week 11 discussion of this course, deep learning. And this course was originally taken by Professor Sudarshan Iyengar, Professor and Head of the Department of Computer Science and Engineering, IIT Ropa, and myself, Ayan Paul. I am a PMRF research scholar from IIT Kharagpur, and I am a PMRFTA for this course. My duties are I will solve some of the question, so that whenever you will be solving your assignment question, you will not feel completely new or completely alienated to the topic. Okay, so that are my responsibilities. But before that, I always prefer to discuss the summary of the week, so that it will be easier for us whenever we are discussing the question answers. Okay. Okay, so let's start with this. So yeah, so what we have read in the course, from week 1 to week 8, we have discussed the theory and the background behind this neural network. Okay, someone is joining. Yeah. From week 1 to week 8, we were discussing the theory or background behind this neural networks. Week 9, we have discussed first application of neural network, that is neural network applied to this natural language processing, NLP. In the week 10th, we have discussed, in the week 10th of the last week, we have discussed this new neural network known as convolutional neural network that we apply to the images. Okay, and in this week, what we will be discussing something called recurrent neural network. Okay, so for that, let us first see what were the limitation of this feed forward neural network or the convolution neural network. Convolutional neural network is also a kind of feed forward neural network only, but the thing is, we have this sparse connection, and we have this weight sharing, and also we have this many different type of layers. Okay, like convolution layer, pooling layer, etc. So it is also a kind of feed forward neural network. So what are the limitation of this feed forward neural network? So first limitation is, whatever you have seen, the inputs of this feed forward and convolution neural network, the size of the input was always fixed. That was the first limitation. For example, you can see in this convolution neural network, the image that will be applied as the input for this convolution neural network, it will be of fixed size. Like here, the image is of size 32 cross 32. Okay, similarly in this feed forward neural network, like that is in this word to vec example, also you can see the image is of specific size. That will be depend on the window size we are taking. For example, window size here we are taking 2, so this is the input size. Okay, 2 into the vocabulary size. Okay, this is your input size. So that is the thing about this feed forward neural network as well as this convolution neural network, that is size of the input is fixed. What is the another limitation is that inputs are independent of the previous or future inputs. Like in this image also, whatever at the time step t, whatever you will be supplied to your convolution neural network, that will be completely independent with the image that you will be fed to your you will fed to your convolution neural network in the future or even in the past. That means there is no dependency between the previous or the future inputs. Okay, that is another limitation of this feed forward neural network or convolution neural network, right? So we have successfully applied this feed forward neural network and convolution neural network for specific examples, but where we cannot apply this. For example, you see this example, the task of auto completion. Okay, auto completion means whenever you are writing something, the software will suggest the word or the letter that will come after what you are typing. Okay, so that is known as auto completion. Okay, task of auto completion, right? So in this task of auto completion, the input size is not fixed. Okay, for example, you can say here, the whenever you are writing one type of input, like one type of word, the letters are of different size. Like deep, when you will write, the letters of size 4, but when you will write another word like learn or machine, the word will be of different size. Also, you can see whenever you will be feeding one input, like D when you will feed, then E when you will feed, this D and this E is dependent on D, right? That is how you will auto complete. Like whenever the D will come, your output should be E. For the next output, the input will be dependent on the previous output. Okay, so that means there is a connection between the this input and the previous input, right? So this is the another thing. So this type of problem is known as sequential learning problem. Okay, so in sequential learning problem, how we can treat this sequential learning problem? We can treat this sequential learning problem is for each, like for a word, for each letter you build a complete neural network. Okay, for D you built a neural network, for E you built a neural network, for this E also you built a neural network, for P you built a separate neural network. But where the problems are, if we build the separate neural network, we have this following problem. Okay, like yeah, there are other example also. For example, this man is a social animal. In this, what we are interested is, we are interested to know the part of speech of this words, like okay, someone is joining. Okay, part of speech of this words, like what is the part of speech of word man is a social animal. So here how it is, like sequentially connected. See, whenever the adjective will come, after the adjective always a noun comes. Okay, so that means this inputs are connected or dependent on the previous input. Okay, another example you can take, whenever you are sequencing a video. What is a video? Video is a sequence of images, right? So whenever you are classifying inputs of a video, that means at each time step there will be a different classification. If you take only one time step, so that cannot classify what exactly the thing is happening. For example, the sequence here is happening in Surya Namaskar, but whenever you will see the last sequence, you can say it is only Namaskar, right? It is not a asana. So that is why here also this sequence learning is important. Okay, now to make a neural network for this type of sequence learning problem, what is our wish list? Our wish list is, first account the dependency between the input. I have told you the input are dependent on each other. So first, what we have to find out? We have to find out the dependency between the inputs. The second thing is account for variable number of input. I have told you, like whenever we are doing that task of auto completion, the deep is 4-letter word, but if machine you will choose, that is a 6-letter word, right? So that is the thing, like whatever the word you will choose, the size will vary. So that is another thing. And last is, make sure that function executed at each time step is same. Again you have to make sure that the function that we will execute at each time step, that will be same. If that is not same, each neural network will be a separate neural network, right? So that also you have to account. So these three things you have to account and make a network from our feed forward neural network to a new thing. So what is the new thing called? New thing called is recurrent neural network, right? So you see this network, these are the two inputs. You can treat it as separate network. This is another network, this is another network. So this orange part is your input, this is your hidden state, or you can say that hidden layer, and this is your output. Okay, So you can just like you have done in the neural network, you can find what is the how s1 is related to x1. Okay, see, s1 is related to x1 and this is x2. Okay, so how this s1 is related to x1 and s2 is related to x2. So this is very simple. Si at each time step, si will be something function of u into xi. That means u is the weight between the input layer and the hidden layer, u into xi plus the bias, and function of that. So that will be your si. Similarly, you can calculate the yi. Yi will be this v into si plus the another bias, that is c. Okay, and the function. Okay, 1 minute. Yeah. So I was talking. Yeah. So yi will be this function of si, v into si plus this c. Okay, c is the bias. So that is the thing. But here what we are missing is, yeah, one thing we have done is each time step we are applying the same formula. That means we have done this step, that is third step. But this two step we have not done, that is account for dependency between the inputs, that we have not done. Account for variable size of input, yeah, variable size of input we have also done, because see, this neural network is for 2, but if we will do the same thing for 10 or 12 inputs, that this network will be same. So this two we have done, that is variable number of input we have done, and make sure the function executed at each time step is same. That two things we have done. But the first thing we have not done yet, that is account for dependency between the inputs. So how that we will done? We will done with a network known as recurrent neural network. Okay, why recurrent neural network? Feed forward neural network means information will go from in the forward direction only, means from the bottom to the top, or from in the forward direction. But in recurrent neural network, what happens is information again goes back. Okay, so that is why it is known as recurrent neural network. For example, if we have just a forward neural network, our network will be like this only. But if we have recurrent neural network, you can see this state is taking information from this x2 input as well as this previous state, that is this state. Okay, that is why we have this weights between the two hidden state, that is w. So this type of network is known as recurrent neural network, or this type of connection is known as the recurrent connection. Previously in the feed forward neural network we have only forward connection, but here the connection are recurrent connection. Now this is the thing. Now how we can write the formulas now? Now as we have connected the hidden state, so our formula of hidden state will change. Okay, how it will change? The formula of hidden state will be, yeah, some kind of function. Let's just leave the function as of now. Let's see what is in the bracket. So in the bracket, previously we have u into xi plus the bias. Okay, so now also we will have u into xi plus the bias. But now what's happening? This w is also coming to our neural network, and this w will be dependent on the previous state. Okay, so that is why we have just adding the term w into si minus 1. So this w into si minus 1 will take the information from the previous step. Okay, someone is joining. Yeah. Okay, so that is the thing. Similarly, in yi will remain same, because yi does not take the w, so yi will be v into this state information plus the bias. Okay, so this is the formula of the recurrent neural network. Okay, this formula previously what I have shown, this is formula of a simple feed forward neural network, but this is the formula of a recurrent neural network. Why it is a formula of a recurrent neural network? Because this hidden state is taking the information from the previous state. For this inclusion of this term, the feed forward neural network gets converted into this recurrent neural network. Okay, now what are the parameters of this recurrent neural network? We have this parameters. Okay, w, u, v, b and c. Okay, b and c are the bias, that is same as the feed forward neural network. U and v are the weights connecting the, u is the weight connecting the input to the hidden state, or the hidden state, and w is the weight, v is the weight from the hidden state to the output state. But w, we have included this w. Okay, w is the weight from the hidden state to the previous hidden state. Okay, so that is the inclusion that we are doing in the recurrent neural network. And why we are doing this? Because we have to solve something known as sequential learning problem. Previously our inputs are not dependent on each other and our input is of limited size. That is why we have used our feed forward neural network or convolution neural network. Convolutional neural network is also a type of feed forward neural network. But now, as our input is not of constant size and our inputs are dependent on each other, that is why we are using this recurrent neural network. So that is the theory behind the recurrent neural network. So up to this, is it clear to all of you? Okay, nice. Now if we have made a network, what is the next step? Next step is always to train the neural network. So how we train the simple feed forward neural network? We train the simple feed forward neural network by an algorithm known as backpropagation.
Backpropagation.
Yeah, backpropagation. Now here in recurrent neural network, what we will do, as now our input it is a sequential learning problem, right? So we have different time steps. So we will apply the backpropagation only, but we will apply this new theorem called backpropagation through time. Now we will also consider at each time step what is happening in the backpropagation. That we have to see in the backpropagation through time. Okay. So this is the thing, these are the dimension. You can see the x is of dimension Rn. Okay, this Si or the hidden state is of dimension Rd. This Yi is dimension k because we have this k classes in the output. Now you know how we can have the dimension of u, v and w. Just yeah, how we can have the dimension of u, v and w? U will be r n cross d, because this input is our n dimension and this hidden state is our d dimension. Similarly, how we can get the dimension of this v will be this d cross k. Okay, and how we can find out the dimension of w will be d cross d. So these are the dimension of various whatever the different inputs, hidden state, or as well as the parameters of the this parameter of this recurrent neural network. Now how we will proceed with the back propagation. So before proceeding with the back propagation, it is always important to check two things. One, what is our loss function? Second, what is our first, what is our output function? Second, what is our loss function? So in all this recurrent neural network, what we do, we generally do this classification problem. Okay, so in classification problem, you know the output function is of softmax function, and this loss is of cross entropy loss. Okay, so you got this output as well as this you got this output function as well as this loss function. Then what you will do, you will just back propagate. Okay, so how we will back propagate? Earlier we were just having the loss function and we are doing dl by d theta. Okay, dl by d theta, whatever theta we have, like. But here as we have this so many L, because we will have this L in this time step, L in this time step, L in this time step, as well as L in this time step. So how many time steps we will have, our loss function will just add up. For example, we will have this L1 theta loss at this time step 1. At this time step 2 we will have L2 theta. In this time step we will have L3 theta, and this time step we will have L4 theta. And if we just add all the L, we will get the loss over the entire recurrent neural network. Okay, this is the loss thing. Now as we are using what type of loss? Cross entropy loss. This is the formula of cross entropy loss. So we will have this true log predicted, right? So predicted is this YTC, and true as true for all this values are 1. That is why 1 dot log YTC, that 1 it is not written. So this is the loss function. Okay, now what are our this parameters that we need to update? The parameters here are this weight, u, v, and the biases, that is biases in this b and biases in this, that is c. So these things we have to update. So we will again do our same thing, that is we will go from dl by we will have to reach from dl to this input, right? So to have this, we have to again use this chain rule, because we cannot directly reach from here to here, because we have so many things in between. That is why we will apply a chain rule. Okay, so first we have to just find dl by dv. That is same like the feed forward neural network, because dl and this output and this hidden state output, or this weight connecting this hidden state to the output, this do not have any other connection in between, so it will be straightforward. That means whatever we have done in feed forward neural network, same thing you have to do. Just we have so many time steps, so just again add a sigma. That means add all the gradient of all the time step. That is this thing. Now what will be dl by dw? Okay, dl by dv is okay, but what will be dl by dw? So to calculate dl by dw, we have to we have in between these states are coming, okay, hidden state or s are coming. So dl by dw, yeah, let's see an example of L4. That means what will be the dl4 by dw will be equal to, okay. So L4, so for that you have to L4, so this is L4, so we are just interested to calculate what will be dl4 by dw. Okay, so for that, as dl4 will be dependent on s4, so you have to see how this s4 is dependent. So L4 will be dependent on s4, s4 will be in turn dependent on s3, s3 will be depending on s2, s2 will be depending on s1, and s1 will be dependent on some constant s0. Okay, this s0 is nothing but bias, so let's just leave s0 for now. So these are the things that your s4 will be dependent on. Now again s4, yeah, we all know s4 is calculated by this formula, w into s3 plus the bias. Okay, this is the formula for calculating the s4. Now to do the ds4 by dw, we will have two things here. One is the explicit terms, and another one is the implicit term. Okay, what is the explicit? Explicit means we just treat all other things as constant. For example, we just say s3 is our constant, b is all know b is at the constant, but s3 we can also choose s3 as our constant and find the ds4 by dw. So that is known as explicit differentiation. That is why we just use a plus sign here. But another thing is called implicit. For example, s3 will be further dependent on, we all know s3 will be dependent on s2, s2 will be dependent on s1. So for that also we have to do differentiation. So for that, this the differentiation that is remaining apart from this ds4 del plus s4 by del w, that differentiation is known as implicit terms. Okay, so explicit terms and implicit terms. Okay, so for example, for sake of simplicity, this we have to calculate, that is dl4 by dw. ds4 by dw, dl4 by ds4 we can calculate directly, because nothing is coming in between. But for to calculate ds4 by dw, we have to do the implicit as well as explicit. Okay, this is the explicit, and this term over here, these are the implicit. Okay, so just if we can calculate the implicit and we have this explicit, we can get the full differentiation. And this algorithm is known as back propagation through time, as we back propagate over the previous step. Okay, in this implicit terms, what we are doing, we are back propagating over all the previous step, that is s3, s2, s1 and whatever s0. Okay, so that is why this algorithm is known as back propagation through time. Okay, so this is the thing. Now another problem of this back propagation over time, we will have this problem of exploding and vanishing gradient. So let's understand what is the problem of this exploding and vanishing gradient. Okay, so this explicit term is okay, but see the thing about implicit term. So whenever we are seeing the implicit term will take many differential term, right? Like dst by dst minus 1, dst minus 1 by del s del st minus 2 dot means into del sk plus 1 by del k, means how many how many of your time step is there, your differential term of this implicit term will take all the states. Okay, so that is why this formula will be like this. Okay, that means if we just open the del s4, here we are only showing for only 4 time step, but in reality there will be many more time step, right? So that is why if we just open the differentiation, our differentiation will be very big, it will take all the states. Now just if we just simplify this, so we have this two thing. One is del sj by del aj, and second is this thing del sj by del yeah, you just see this will be more clear. So whenever you will be yes, let's again see this. So what we are doing in this formula, this thing is same, just we are writing from j equals to k to t minus 1 term. So whenever you will write k equals to j equals to k, so just we will put j, and as we are doing from t minus 1, so that is why del s j plus 1. Okay, so that we are writing in the another notation. And same thing, you can just focus on this, but to write this big term in a multiplication formula, so this is the formula, and this is the formula, this is the simple for symbol for multiplication. Like we use this sigma for this addition of many step, like t1 plus t2 plus t3. Whenever we will write t1 into t2 into t3 into t4, we will write this we will use this symbol of for multiplication. So as we are writing I equals to 1 to n, so just what we do, t1 plus t2 plus t3 plus t4, like that. Whenever we will do I equals to 1 to n, we will write t1 into t2 into t3 into t4, like that. So same thing, it has been written, this has been converted to this. Okay, so this term has some problem. What is the problem? If we just open this term, okay, if we just open this term, so this term can also be written as like this, del sj minus 1 to del sj. Okay, so this del sj by, yeah, this will be your hidden state thing. Okay, so that is w into sj plus b, that means this. Okay, this is your thing, like aj is the subsequent like this is your s0, and we are calculating s1, so for calculating s1, this will be your formula. Okay, w into sj plus b. Now what will be your sj? Sj is nothing but just the sigma of whatever is in the aj. Okay, that means whatever you will calculate in s1, just put the sigmoid function and you will get the output of this hidden state. Okay, so we have this two things. Now to break this, we can just break this and write like this, del sj by del aj into del aj by del sj minus 1. Whenever we will do this, whenever we will do del sj into del aj, so this del sj into del aj, this can be written in the form of matrix. Okay, this matrix we can write, and in this matrix only in the diagonal terms we will have values. In the non-diagonal terms we will not have values, because you can see this del sj2 by del aj1, as this is not this aj is not related to sj2, so that is why this term will be 0. So only in the diagonal term this things will remain, the other terms this places will be 0. Okay, so this is the thing. So this is the first step. What will be the next step? Whenever you will be do del aj by del sj minus 1, for that only you have w terms in between. Okay, so like this, del aj by del sj minus 1, your answer will come only with respect to w. So your final answer will be the differentiation of this term sigma aj and into w. So that will be this can be modified to this thing. Okay, let me erase this to have a clarity. Yeah, your thing will be like this, your this thing can be written as this. Okay, diagonal of this, that means sigma aj. Sigma aj is the function of that whatever will be the hidden state, and differentiation as we are doing del, so that is why differentiation, as and the terms are only in the diagonal, that is why diagonal. And into, if we just open this, we will have this w. Okay, so our this thing is converted into this term. Okay, now the problem is in this term. Okay, we problem in both the terms. So first let's see this term. Okay, what is the problem in this term? If this value is so large or so small, okay, normally we have a problem of this vanishing gradient for here. Okay, so if this value is so small, what will happen is, as we keep on multiplying, we are not multiplying for one time step, we are keeping on multiplying for like 100 or 1000 times step. So if this value is very small, our gradient will be very less. Similarly, in case of w, if our w will be very large, if our w will be very large, what will happen is we have a problem of exploding gradient. So let me again repeat in a simpler terms. So we have seen this back propagation over the time. Okay, this back propagation over the time has two things that we have to do. One is the explicit term and one is the implicit term. Explicit term we do not have any problem, but we have a problem with the implicit term. What is the problem with implicit term? Implicit term will take differentiation from many time steps. If you will have 100 time steps, so it will take differentiation from this 100 time steps. Okay, first thing. Second thing, if we just simplify this into this formula, so we are having two parts. One is simply the weight that is associated. Second, we will have the differentiation over whatever is coming to the state. Now differentiation over whatever is coming to the function of whatever coming to the state. So the function we are using in this recurrent neural network, that is we are using the sigmoid function. Now what is the value of the sigmoid function? What is the maximum value of differentiation of a sigmoid function? So maximum value of differentiation of a sigmoid function is 1 by 4. Similarly, maximum value, sigmoid means logistic. Okay, sigmoid means all the s-shaped function is known as sigmoid function, but generally if we are telling about sigmoid function, it is logistic function. And we have a second type of sigmoid function that is known as tan-h function. So the maximum value of this sigmoid function is 1 by 4, and maximum value of this tan-h function is 1. Okay, so yeah, so we have maximum value for this. Okay, someone is joining. Yeah, we have this maximum value of this sigmoid function as 1 by 4, and maximum value of this tan-h function as 1. So whenever we are doing this, and we are just showing for one sigmoid function. Okay, differentiation of one sigmoid function. But in our this implicit term, we will have differentiation of like 100 sigmoid function. So 1 by 4 into, let's say the maximum, 1 by 4 into 1 by 4 into 1 by 4 into 1 by 4. Whenever you will be doing 100 times, your this gradient will vanish, right? Because the value will be very small or very close to 0, so your gradient will vanish. Second thing, in case of w, if we are choosing very large w, what will happen is, our as we are again multiplying this term again and again, so if we are choosing like 1000, value of w as 1000, so 1000 will be multiplied like 100 times, so our this gradient will explode. Okay, so these two are the problem. We have this problem of vanishing gradient problem, and we have this problem of exploding gradient problem. Vanishing gradient problem is because of this function. Okay, because we are using the sigmoid function, so that is why we will have this problem of this sigmoid gradient vanishing gradient problem, right? Because the maximum value of differentiation of a sigmoid function is 1 by 4. That is the maximum value. Okay, so let's say the maximum value is only coming, so 0.25, if you will do 0.25 100 number of times, what will happen is our gradient will be very small and it will vanish. And second thing, if we are using a very large value of w, what will happen is, if we are just multiplying those gradient again and again, what will happen? We will have this problem of exploding gradient. So what is the solution of this exploding or vanishing gradient? Simple. If we can just limit the multiplication term, then we will just we can get rid of this vanishing as well as exploding problem. For example, this term is of 100 terms, right? But if I just truncate it to 10 terms and just leave the 90 terms, what will happen? We will not have this vanishing as well as exploding gradient problem. Vanishing and exploding gradient problem is mm, only happening because we have so many differential terms, right? So if we can just truncate our network, so what we can just get rid of this vanishing as well as exploding gradient problem. So this is the thing about vanishing and exploding gradient problem. So just if we use this truncated backpropagation, that means we just truncate a network and we just do the backpropagation. In that case, we will not have this problem of vanishing as well as exploding gradient problem. Okay. So is this clear to all of you? Why we have this vanishing as well as exploding gradient problem? Okay, nice. So let's move on to the next thing, that is selectively read, selectively write, selectively forget, the whiteboard analogy. So this is the figure of the RNN. The state SI of a RNN record information from all the previous time. Okay. So at each new time step, the old information get morphed by the current information. For example, if I take this information of S4, that will be this X1, like what we have seen in the case of this convolution neural network. For each layer, we can get the whenever we are doing those last thing, that is pattern recognition, for each layer we are getting the information, okay, from the input information, right? For each layer, if I just flatten out the layer and try to see the image on that layer, we are getting the informations in this convolution neural network. But in this case of RNN, what happens is in for this each hidden time step, what we are morphing the hidden state with the information from the current state. Okay, so if I just want to have the information of x1 and s4, it is very difficult because we have morphed it by x2, x3 and x4. So that is the problem of this RNN. So one could imagine that after the t time step, the information stored at time step t minus k gets completely morphed. So that is the thing, that is information at the time step before the original time step will get morphed, because we at each time step we are bombarding it with the input of the current state. So that is the problem of this RNN. Okay. A similar problem occur when the information flow backward. That means whenever we are doing the back propagation, the similar problem will occur. Why the similar problem will occur? In the back propagation also, whenever we are just propagating back, what will happen is the error or loss at the loss after the output, that should depend on each that should depend because of each input layer, right? The loss of the output should depend on each input layer, but as in each input layer we are just bombarding the new input, what will happen is it is very hard to assign the responsibility of the error at time step t to the events that occurred at time step t minus k. This responsibility is of course in that form of gradients, and we studied, yes, that is the logic, that whenever we are just propagating back, again the loss function will depend on each input, each hidden state, right? So the loss, as we are bombarding each hidden state with a new input, so our loss function will also won't be fully dependent on the loss of the particular layer, right? So these two are the problem of the RNN. Okay, someone is joining here. So these two are the problem of this RNN. Okay, so to get rid of this, we can use this theory called known as whiteboard analogy theory. You know what we do in whiteboard, we just write something, just compare this to a fixed size whiteboard that you use to record information. At each time step, we keep writing something to the board. Effectively, at each time step, we morph the information recorded till that time. After many steps, it would be impossible to see how the information at step t minus k contributed to the time step t. That means what we do in the whiteboard, we just write something, we just read something, and after that what we do, we just delete something. So after 3-4 deletion, if you just want to know what is the information written in the first time step, it is impossible to get, right, because we have morphed it many number of times. So that is how we can have the analogy of whiteboard with the RNA. Now continuing our whiteboard analogy, suppose we are interested in delivering an expression on the whiteboard. We follow the following strategy at each time step. We selectively write on the board, we selectively read already written content, and we selectively forget. That means we erase the information. These are the 3 steps that we always do while writing or while doing anything on the whiteboard. First we selectively write on the board, then we selectively what we read on the board, and then we selectively forget or erase some of the content. Okay, so that is the thing. Now say like board can only have this 3 statements at a time. We have this a equals to 1, b equals to 3, c equals to 5, d equals to 11, and what we want to do, we want to compute this thing, that is ac into bd plus a plus ad. This thing we have to compute, but this is a condition. Say in our board we can only write 3 statements at a time. Okay, so what can be the statement? Statement can be AC, BD, BD plus A, then AC, BD plus A, AD, and AC, BD plus A plus AD. Okay, this is the full statement. So these are the statement that can be written. So let's say how we will selectively write. So how we will selectively write? There may be many steps in the derivation, but we may just skip a few. In other words, we select what to write. Means we can write so many things, but what we will do, we will just select few and we will skip others. So what we will select, we will initially select AC equals to 5. That means AC we will select, and we will select BD. These 2 things we are selecting first. Then what we will do, we will selectively read. Okay, selectively read, we will just in the selectively write only, what we can do, while writing one step, we typically read some of the previous step we have already written and then decide what to write next. Okay, so AC, BD we have written. Then what we will do, AC and BD we have written. Now what we need to do, we need to have this BD plus A. That is why in this step we can write this BD plus A. For example, at step 3, information from step 2 is important. Okay, so for step 3, this is our step 3, like we can only write 3 statement, but in step 3 we know this information from the step 2 is important. If we do not have this BD in the step 2, how we can write this BD plus A? So in other words, we select what to read. So again I am repeating, in selectively write we just write few statements. In selectively read, what we will do, we write the third statement, but third statement can be only written after reading the second statement. So that is why we are selectively reading in this step. Now third step, what we have to do, we have to selectively forget, right, because we need to have this information, that is AC, BD plus A plus AD, right. But in this 3 things, if you just read these 3 things, our board is already occupied by 3 statement, but there is a condition that our board can only have 3 statement. So now what we have to do, we have to erase some and then write some. So what we will erase, what we can erase, we have this BD plus A, okay, and we have this AC and we have this BD. Okay, so we can just write, we don't have, we don't have AD. So first we can write this AD, okay, and then we have this AC and BD plus A. So we can just combinedly write this AC and BD plus A, and then we can concatenate this 2 and write AD plus AC, AD plus AC, BD plus A equals to whatever that will come, that is 181 is coming. So this is the third step. So what we are doing in the third step, once the board is full, we need to delete some obsolete information, like the board was already full in the selectively read, because we have written 3 statement, and we know the board is can only contain 3 statement. So now we need to delete some of the obsolete information that is coming again and again. Okay, that information we can erase. But how do we decide to do this? We will typically delete the least useful information. So least useful, what we find is least useful, we will delete. Like BD here is also there, BD here is also there, so this we can delete, BD just we can delete. And second, we can add on and make whatever our complete sentence is. So these are the three strategy that we follow in the whiteboard. One is selectively write, second is selectively read, and last is selectively forget. So these are the three things that we use in whiteboard. Okay. So there are other scenarios where we can motivate the need for selectively write, read, and forget. In RNN also we can do this, that we will see in the next slide. Okay, that is, we can use the same concept in this two recurrent neural network. One is this long short-term memory LSTM network, and second is that gated recurrent neural network, gated recurrent units, or GRUs. Okay, these are the two things for that thing just that we have just read the institution, or we have just understood the institution. That thing we will try to implement on a recurrent neural network. Okay, and when we will be implementing these things in a recurrent neural network, we will have two different kind of recurrent neural network. One is the long short term memory LSTM, and second is the gated recurrent units. Okay, so can we give a concrete example where RNN also need to selectively read, write, and forget? So, for example, see this example of machine translation. Okay, machine translation. No, this is the, yeah, this is the sentiment task for predicting sentiment of the review. Sentiment means positive or negative. Means you will be giving a sentence to your this recurrent neural network, and you want as a output whether the sentiment is positive or negative. Okay, so this is the task. So in this task, there are some things that needs to be understood. First, RNN read the document from the left to right. Yeah, RNN will be if we just put a simple RNN, what the RNN will do, RNN will read the document from left to right, and after every word it will update the state. Okay, like it will first read the, and it will update the state, then it will read first and it will update the step. Similarly, it will read each word from left to right, and it will keep on updating the step. Okay, by the time we reach at the end of the document, the information obtained from the first few words is completely lost. Now what will happen is, if you are considering your human brain and you are comparing with this RNN, what will happen is, you don't just do the calculation like that, right? You what you do, you don't just listen each word and then give your perspective or give your this output. You don't do this, right? You just read the complete sentence. You see or you feel what is the important thing that is the sentence. For example, you see this review, the first half of the movie was dry, but the second half really picked up at pace. So in this whole statement, what is important? One was the first half is important, and first half dry is important. What is important is second half is important, and then picked up with pace is important. So some of the information is only important. If you will just read the first word and give the output, that does not make any sense. So that is the problem that we are facing in the traditional RNA. That means at each input or each state it is giving an output that we do not want. Okay, and second thing, the vocabulary can be very large, and after a large vocabulary only it is giving output. That is also problem, because we know in a vocabulary some words are only important, the other words are not as important like that. So by the time we reach the end of the document, the information obtained from the first few words is completely lost, because at each time state we are bombarding it with a new input. So the information will be completely lost. So in this case, again, what we will use are this selectively read, selectively write, and selectively forget thing. Okay. So ideally, what we want to do, forget the information added by the stop words. So whatever the stop words is coming in between, like of, these are not important, right? So we want to forget this words first. Then we want to selectively read the information, like what is important, dry is important, then picked up pace is important, these are more important than the other words, so we need to selectively read. Second, we need to selectively write new information from the current word to the string. Okay, last we need to combine everything, and we need to think. So these are the things we need to do. First, we need to just forget the stop words that are not necessary. Second, we need to only selectively read the words that are of importance. And last, we need to just combine different words and selectively write our output. Okay, by this uh, we can reach our output. Okay, so this is the analogy of this selectively read, write and forget in a RNA. Okay, now recall the blue color vector. This blue color vector are nothing but your state, right? So this state can be think of nothing but your whiteboard. Whiteboard also we have this problem of space, right? We can only write three sentence or four sentence like that. This, so we have this problem of space. In the RNN also, in this blue color box or the hidden state, we have this problem of space, because after each blue whenever the input is added to each blue, yeah, each, like you just focus on this blue box or this hidden state. This hidden state will take the information from the new state, a new information from the input from the new state, as well as the information from the previous hidden state also. So if I go to this hidden state, this hidden state has the information all this hidden state as well as this state. So as we are keeping on adding this blue step or this hidden state, what is happening is, as we keep moving forward, our hidden state gets bombarded with more information, just like our whiteboard. Our whiteboard, as we are writing this information, similarly in this writing this information, our whiteboard got full. For here also, as we keep on going from one hidden state to another hidden state, the hidden state will take more memory. So that is the thing. So this state is analogous to the whiteboard, and sooner or later it will get overloaded, right? So as we move forward, this will get overloaded, and the information from the initial state will get morphed beyond recognition. So what is our wish list here? Selectively write, selectively read, and selectively forget to ensure that this finite size state vector is used effectively. So that is our wish list. So to do this, we will be focusing on our first network, that is long short term memory, or LSTM network. So LSTM, how we can selectively write the information. So recall in the RNN we use this st-1 to compute this st state. Okay, so yeah, this you all know. This is the formula to get the information of the st. What you need to do, you need to multiply the weight, this w, into information of the previous hidden state, plus what you need to do, you need to do u into the information that is given in the given from the input of this state. So this is the thing. So we are just ignoring bias as of now, but now instead of passing st-1 as it to st, we want to pass write only some portion to the next state. Okay, so previously what we are doing, we are just giving the st-1 completely, but now what is our idea? We will just give some portion of st. Okay, now some portion of st does not mean we will give some state, and other state we will keep 0. If we will do this, then we will lose some amount of information. So rather than, what we can do, we can have the weighted thing. That means we will give some weighted information to that state. That means if we can just assign a value between 0 and 1, and we just multiply to the state. Previously what we are doing, we are giving information for all the state. We are giving information of this state, this state, this state, this state, this state, right? But here now what we are interested in do, one thing we can do, we can just 0 some of the state, and we can 1 some of the state. But that, what the problem with that, whenever we will be calculating the back propagation through time, in that there will be a problem. Second problem is, we are losing many information. That is why our idea is not to give the full information for all the state. We are just assigning the value from 0 to 1, and we are giving some sort of information to the next state. So this is the thing. We introduce a vector ot minus 1. How we will do this? We will just introduce a vector ot minus 1 which decide what fraction of each element of st minus 1 should be passed to the next state. Now each element of ot minus 1 gets multiplied with the corresponding elements to get this st minus 1. Each element of ot minus okay. Just forget this. Well, the RNN has to learn ot minus 1 with the other parameters. Okay. Now the thing is, you are introducing value between 0 to 1. Now this 0 to 1 value should also be learned. Okay, because until it is learned, we cannot just fed it. We do not know which information is important and which information is not important. So what we need to do, we need to also have this parameter, have this additional parameter for this ot minus 1. Okay, so for what are the additional parameter? We are adding this w naught, u naught, and b naught. These are the parameters we are adding. Earlier we have this parameter w, u, v. Now we are using parameters w naught, u naught, and b naught whenever we are doing this ot minus 1 to the previous hidden state. So this is the thing. Now second thing is selectively read. How we can selectively read? We will now use ht minus 1 to compute the new state. Okay, at next time step, because earlier our formula was ht minus 1, but now the ht minus 1 is converted to this ht. Okay, now we will use this ht minus 1 to compute the new state in the next step. We will also use this xt, which is the new input to the step t. Okay, so this is the thing. So now our value will get changed. Earlier it was ht minus 1, but now it will be ht minus 1. This ht minus 1 we will get where ht minus 1 we will get from this ot minus 1, because we have done this ot minus 1 to this previous state ht minus 1. So whenever this ot minus 1, or I have already told you, whenever this ot minus 1, that is the value between 0 and 1, this will be multiplied to previous state ht minus 1. The new state we are getting, we are terming it as ht minus 1. Now this state will get changed. This earlier it was ht, but now it is ht tilde. Okay, because earlier we are using ht minus 1, that is why it is ht. Now we are using the ht minus 1, that is why this got changed to ht tilde. Note that w, u, and b are similar to the parameter that we are using in RNN. Same thing. This ht thus captured all the information from the previous state ht minus 1, and this is the current state xt. However, we may not want to use all this new information and only selectively read from it before constructing the new cell state st. Okay, so if we are completely doing this st like this, so what we are doing, we are not selectively reading the term. Okay, now what we are interested to do is, we are also interested to read some of the essential information, right? Because you just understood in the whiteboard analogy, first we are writing something, then we are selectively reading the thing. Okay, and then we are adding the new thing. So in this step, what we need to do, we need to selectively read the thing. How we will do? By the help of this input gate. Okay, this is the formula of the input gate. So by the help of this input gate, what we can do, we can selectively read the state. Okay, so this is the thing. So so far what we have done, we have this previous state ht minus 1. We are putting this output state ot minus 1. This state is known as this output state, or output gate rather, we can tell. So output gate, the ot minus 1 we are applying to this ht minus 1, and we are arriving to this ht minus 1. So this is portion up to selectively write. Okay, after selectively write, what we have done, we have this current temporary state, that is ht tilde, because we are using the ht minus 1. We will apply this input gate, and whenever we are applying this input gate, we have this selectively read. So selectively write we have done, selectively read we have done. Now we have to see how we can do the selectively forget. So how do we combine this ht minus 1 and ht tilde? So we have this previous state ht minus 1, but after having our this selectively writing gate, our temporary state is st tilde. So how we can combine it? So we here is a simple but effective way in combining this. St will be equal to st minus 1 plus it into, that is the input of or the selectively read information. We just, if we can just plug the selectively read information to this st minus 1, we will get the current state, that is st. But we may not want to use the whole st minus 1, but forget some of the parts, because again if we just using this st minus 1, there is no logic of have this selectively write read gate, right? Because again we are using the whole big st minus 1. So best thing is forget something. So how we can do? We can do by having the next gate known as forget gate, just multiplying this ft with this st minus 1, and we are getting the original state, that is this st. So this is our original state. Okay. So if I just sum up what we have done, we have used three different gate, and we have this three different state. So first we have used this output gate. Okay. Whenever we have this whenever we are applying this output gate, our st minus 1, our st will change to this temporary st tilde. Okay. And then what we are doing is we are applying this input gate. Okay. And whenever we are applying this input gate, we have this thing, that is this st, we are arriving this thing. Okay. And then we will apply this our forget gate, and whenever we are applying this forget gate, okay, I think this is something written opposite. Okay. So let me again erase this. Okay. So see, whenever we are applying this output gate, this is our st, that is the hidden state. Okay. And then we are applying this input state, so this is the thing. And whenever we are applying the output state, this is our output. Okay, we cannot explain like this, so again let me erase this. Yeah. So just you can just imagine like this. We have this 3 gate, that is the output gate that we are just using here, that is the output gate. Whenever we have this output gate, we are arriving this st minus 1. Okay. This is the thing. And then we are applying this selective read gate. Whenever we are applying this selective read gate, that is the input gate, we are arriving this it.st. Okay. It.st. We have this st previously, and we are doing this it.st, and we are arriving at this. Okay. St equals to st minus 1. We are arriving at this state. And then whenever we will be applying the forward state, we will get the forget gate, we will get the total output, that is this thing. So yeah, we have 3 gate, and we have this thing, 3 gate and 3 state. What are the 3 state? This is the first state, this is the first state, let me write this is the first state, this is the second state, this is the second state, and this is the third state. So we have 3 gate, 3 state. What are the gate? Input gate, output gate, forget gate. What are the state? This is our first state, this is our second state, and this is our third state. So this you have to remember. So complete thing, this network is known as LSTM, or the long short term memory network. Okay. LSTM has many variant, which has included different number of gates and also different arrangement of gates. So this is you have seen one variant of LSTM. There is one another variant of LSTM, popularly known as gated recurrent unit. Okay. So gated recurrent unit. Gated recurrent unit, we have less number of gates. Earlier we have 3 number of gates. Here we have only 2 number of gates. That is, only we have output and input gate. Our no explicit forget gate. The forget gate and input gate are tied. Okay. So in the input gate only, we are just tying the input gate and forget gate to make the input gate of this GRU, or gated recurrent unit. The gates depend directly on st-1 and not intermediate st-1, as the case of LSTM. Also state, we do not have ht state here, so that is why it only have 2 states. So some things you have to remember from this LSTM and GRU. LSTM has 3 gate, 3 state. This GRU has 2 gate, 2 state. So this is the main thing you have to remember. This GRU does not have this forget gate. That is why it does not have another state. It is doing its calculation in only 2 states. Okay, so this is the thing regarding this LSTM long short term memory and this gated recurrent unit. Okay, so this is the thing. Okay, so is this clear to all of you? At least if it is not clear, at least you got the institution what we are doing. Is it clear? Am I audible? Okay. Now let's move on to the next thing, how this LSTM avoid the problem of vanishing gradient. Yeah, exploding gradient we cannot do anything because exploding gradient directly depends on your weight. Okay, but vanishing gradient depends on the this gradient calculation, right? Gradient at each time step calculation. So what does this thing is doing, this LSTM is doing, institution, during the forward propagation the gates control the flow of information, right? So whenever we are having the forward propagation, the gate will control the flow of information. We are not writing the full thing in the next stage, we are just selectively writing, selectively reading and selectively forgetting, right? So we are not writing the complete information of the state, we are doing these three things. So during the forward propagation the gate control the flow of information. Second, they prevent any irrelevant information from being written to the state. Similarly, during the back propagation, they control the flow of gradient. Yeah, back propagation also they will control the flow of gradient. Earlier gradient will be very large, but now we are just selectively reading the gradient as well as selectively writing the gradient and selectively forgetting the informations also. So it is easy to see that during back pass the gradient will get multiplied by the gate. Earlier we are taking the long gradient like 100 terms like that, but as now gates are applied, so our information will be very shortened, and if our information will be shortened, we will not have the problem of this vanishing gradient. Okay, more information and more derivation can be found in your lecture note, but this is the institution. Okay, earlier why we have this problem of vanishing gradient, you can see here also, again I am just showing you, like here also you can see, as we have this long chain of this deltas, that is why as each state we are just taking the full information from the previous state, we have this problem of vanishing gradient. For example, the vanishing gradient, why vanishing gradient, because this will be differentiation of the function, and function here we uses this function known as sigmoid function. So what is the maximum value of sigmoid function? That is only 0.25. So 0.25 we will multiply 100 times, then our gradient will be very small and it will vanish. So that is the vanishing gradient problem. But now as we are multiplying gate with the forward propagation, so this will help in the backward propagation. Okay, why this will help in the backward propagation? Because whenever we will do backward propagation, we will not have this full long chain of gradient. Okay, we are just applying gate at each stages, that is why our information will get shrink, and as our information will get shrink, if also we will have a very small value of gradient like 0.25, earlier we are multiplying it 100 times, but now if we are multiplying it like 10 times or 20 times, we will not have this problem of this vanishing gradient problem. So this is the theory of this week. Okay, so is the institution clear to all of you? And again in this lecture also, so let's move on to the question answer. Okay, so let's move on to the question answer, the topic on which week 11 assignment question are based. First, this sequence learning problem. Second, recurrent neural network. Third is the back propagation through time. Fourth is the analogy of selectively read, write and forget. And fifth is the two type of RNN. One is the LSTM and second is the GRUs. Okay, that is gated recurrent units. So this is the first question. Again I am requesting please illustrate as max value of logistic function as 1/4. Yeah, so max value of logistic function, so let me show you. Yeah, so max value of logistic function is 1/4. So what is the derivation of the logistic function? You can just see in your note, the derivative of logistic function is fx 1 minus fx, right? So fx 1 minus fx, the maximum value of fx into 1 minus fx will be equal to 1 by 4. Okay, that you can do by your that calculation. You just do by the del by del x of this, and you can find the minima and maxima value. So minimum value will come 1 by 4. Okay, sorry, maximum value will come 1 by 4 only. Okay, so this is the thing. So you can just check your calculation, and you can just refer to that back propagation in the lecture 3, I think lecture 3 back propagation. There you can see the what how you can just how you can derivate your this logistic function. Derivation of logistic function comes fx into 1 minus fx. Okay, so maximum value of fx into 1 minus fx is this 1 by 4. So this is the thing. Okay, so this you can check. So this is the first question: for which of the following problem RNN are suitable? Again, I request everyone to just see the question, guess the solution, and then we will discuss. So for which of the following problems are RNN suitable? Generating a description from a given image. B. Forecasting the weather for the next n days based on the historical weather data. Option C. Converting a speech waveform form into text. And option D. Identifying all objects in a given image. So someone is telling B and C. B is forecasting the weather data for next n days based on the historical weather data. Yeah, as this consists of next n days we have to predict. So weather also, it is the inputs are dependent on previous day. So that is why it has some relationship of the current input has some relationship with the previous input. So that is why B is right. Okay, and also we have to predict the weather for the next 10 days. So this is a sequential learning problem. So that is why RNN is applicable to option B. Now what about option C? Converting our speech waveform into the text. Speech waveform, whenever we are talking about speech waveform, this speech waveform is also a kind of this sequence learning problem. Okay, so this is the thing. This speech data is sequential. Audio waveform vary over the time. Okay, audio waveform always vary over the time, and RNN are effectively useful for speech recognition. So option C is also right. Let's see option A, generating a description from the given image. So whenever you are generating description from the given image, you will typically involve two steps. One, you have to extract your image feature by CNN. Second, you have to use RNN to generate this textual description. So this consists of both CNN as well as RNN. So here the thing is asking following problem are RNN suitable. So you can say this is partially right. Yeah, RNN use, but before using RNN we have to apply the CNN. Okay, so this is the partially you can say correct, but as it is RNN suitable, so let's say it is correct. Okay, and option D, identifying all objects in a given image. So identifying all object in a given image, you just use the simple classification problem. That is the you can use the simple CNN and get the results. That is why RNN is not used for identifying all object in a given image. You can just simply use the CNN and get the results. Okay, so that is why this option D is the wrong answer. Okay, so option A CNN plus RNN, option B RNN, option C RNN, and option D CNN only. Okay, so option D is all not correct. Option B and C are correct. A is partially correct. CNN you have to first apply CNN and then you have to apply RNN. So A, B as well as C can be written as the correct answer. Okay, so is this clear to all of you? Clear, right? Okay. Now let's move on to the next question. What is the basic concept of recurrent neural network? Use a loop between input and output in order to achieve better prediction. Use recurrent feature from the dataset to find the best answer. C. Use loops between most important feature to predict the next output. And option D, use the previous input to find the next output according to the training set. So yeah, option D is correct. Okay, option A, it is simple NN only. Use a loop between input and output. We always use a loop between input and output, so that is the feature of this CNN or normal neural network. Use recurrent feature from the data set to find the best answer. So that also does not make any sense. We do not just use the recurrent feature from the data set, so that also does not make sense. Option C, use loop between the most important feature to predict the next output. So loop between most important feature to predict the next output. This is partially can be said correct, but answer D is correct. Use previous input to find the next output according to the training set. This is the most appropriate thing. Okay, use the previous input to find the next output. Okay, because in hidden state the current hidden state is depending on the previous hidden state, and that in turn is dependent on the previous input. So option D is the most appropriate option. Option C, use loops between the most important features to predict the next output. So this cannot completely be ignored. This cannot completely be ignored. Use loop between the, that means in the data set it is using loop, but yeah, it can be told, right, and RNN can be applied on this. Use the loop between the most important feature to predict the next output. Yeah, that can be right, but it cannot be right for the traditional RNN. RNN takes all the inputs. Okay, it will take all the input from the previous step. Okay, not most important feature. Most important feature, this will be in the case of your this LSTM and GRU. So this is partially correct. This is not totally correct. So that is why option D is the correct answer. Okay, D is the correct answer. Here it has been told only for RNN. There is no mention of this GRU or this LSTM. That is why option D is the most correct answer. Okay, so this is the thing. So is it clear to all of you? Now let's move on to the next question. What is the main advantage of using GRU over the traditional RNN? Option A, they are simpler to implement. Option B, they solve the vanishing gradient problem. Option C, they require less computational power. Option D, they can handle non-sequential data. They solve the problem of vanishing gradient. Yeah, they are not simpler to implement. Why they are not simpler to implement? As number of parameter will increase. For this, all this forget gate, output gate as well as input gate, we are adding number of parameter, right? You have seen in the output gate also, we are adding number of parameter. This u naught, v naught, w naught, it has been added. So that is why, as we are adding more number of parameters, so they are not simpler to implement if we are compared to RNN. Yeah, they solve the problem of vanishing gradient, but as again we are using more number of parameter, that is why they will require more computational power. Okay, so that again this is false. They can handle non-sequential data. So this we are only using GRU, we are only using for sequential data only, so that is why this is also false. Okay, so option B is the correct answer. Okay, so they are simpler to implement. GRU have few parameters than LSTM. They are still more complex than basic RNN. Yeah, they are again complicated because we are adding more number of parameters. They requires less computational power. So if we are comparing GRU with LSTM, yes, they are efficient, but simpler RNN we cannot say because number of parameters are increasing, and we are using RNN, GRU or LSTM, they are variant of RNN. So RNN we are only used for sequential data. So they can handle non-sequential data. This is wrong. So option B is the correct answer. Okay, this is the thing. So is it clear to all of you? Okay. Nice. Yeah. The statement that the statement that LSTM and GRU solve the problem of vanishing gradient and exploding gradient and RNN is option A true and option B false. option B false, right? This LSTM as well as GRU, they will solve the problem of vanishing gradient, okay, because as we are applying gates to we are just narrowing our this term, that is implicit term, right? Explicit is same, but implicit term we are reducing, so that is why it will solve the problem of vanishing gradient. Exploding gradient is always related to W, okay, that is the parameter that is associated with the hidden state, okay. So that is why this exploding gradient will fully depend on W, and W we are not doing anything with W is remaining constant for this RNN as well as this LSTM and GRU. That is why exploding gradient, we cannot say anything about the exploding gradient, but LSTM and GRU will solve the problem of this vanishing gradient. So option B is the right answer. It is false. Okay, LSTM and GRU only solve vanishing gradient. We cannot say anything about this exploding gradient problem. So this is what has been written. Yeah, exploding gradient problem happens when gradient becomes excessively large. So we cannot say anything about the exploding gradient problem. But vanishing gradient problem, yes, LSTM and GRU solve the problem of this. Solve the problem of this vanishing gradient problem. So this is the thing. Used to regulate flow of information, so retain long-term dependence. This is gradient from shrinking too much, shrinking too much during the backpropagation, effectively solving the vanishing gradient problem. Exploding gradient problem happens when gradient become excessively large, causing instability. That is already different to depends on W. So LSTM and GRU do not inherently prevent this exploding gradient problem. Instead, technique like I have told you, like gradient clipping, or this you just truncate this your RNN. If you just truncate this RNN, that can solve the problem of the exploding gradient problem. Okay, so this is the thing. So option B is the right answer. So is it clear to all of you? Now we construct a RNN for the sentiment classification of text, where a text can have this positive as well as negative sentiment. That means in the output we will have two classes. One is the positive sentiment and second is the negative sentiment. So output will have two classes. Suppose the dimension of one hot encoded word, that is the input dimension, that is 100 cross 1, and dimension of state vector SI is 50 cross 1. What is the total number of parameter in the network? Don't include biases also in the network. So biases we should not include. We just want to know how many number of weights are there. That weights will be number of parameter, because in this network we do not have biases. So that is the question. So how we will solve the question? So first you will see this layer, that is the input layer and the hidden layer. Okay, this hidden layer, and then hidden layer, then you will say the output layer. So input layer you have this, suppose the dimension of one hot encoder was 100 cross 1. Okay, 100 cross 1 is the dimension of one hot encoder, and in the hidden state you will have this vector 50 cross 1. So how many number of parameter you want? 100 to 50, that means 100 into 100 into 50. Okay, 100 into 50, that is 5000 number of parameter between this input state and the hidden state. Now output, I have told you there are two classes. One is the positive sentiment and there was the negative sentiment. So it is 2 cross 1. So how many number of parameters here? Here it is 50 cross 100 parameter, that is 5000 parameter. Here you have 50 cross 2 parameter, that is 5. Sorry, so spare my writing. 50 cross 2, that is 100 number of parameter. So in between input and hidden state we will have 5000 parameter, and between this hidden state and output state we will have 100 parameter, that is 5100. But what we are missing, this is a structure of ideally neural network, but now we have to construct a RNN, that is recurrent neural network. Recurrent neural network, we also have this connection between the hidden state. So H will be connected to H. So H has 50 cross 50 parameter, here also 50 cross 1 size, and this H will also have 50 cross 1 size. So here the number of parameters is 50 cross 50, that is 2500. Okay, so here we will have 2500 parameters. So input to hidden state we have 5000 parameter, hidden to hidden state we will have 2500 parameter, and hidden to output state we will have 100 parameter. So just sum up 5000 plus 2500 plus 100. So that will be your answer, that is 7600. Okay, 7600 will be your answer. Again I am repeating, 5000 is the parameter between input and the hidden state. 2500 number of parameter between hidden and hidden state, and hidden and output state we will have 100 number of parameter. So 5000 plus 2500 plus 100, that will be 7600. Okay, so 7600 is your answer. Is it clear to all of you? Number of parameter, it is very easy, I think. If it is not a RNN, if it is just a CNN, sorry, not CNN, if it is just a NN, how many number of parameters will be there? If it is only NN and not a RNN? No response. If
250.
how many? 250. Can you please repeat? Okay, so no answer. So if it is just a NN, we do not have this structure. That is, there is no connection between the hidden state. Okay, so that is why this we do not have. So that is why our network will have 5000 plus 100, that is 5100 parameters. Okay, because in neural network we do not have a connection between the hidden state. That means I am not talking about layer, different type of layer. I am talking about only one layer. In simple neural network, you will have input layer. Sorry, just let me erase it. Yeah, you will have only input layer. You will have this hidden layer, and you will have this output layer. Only this. Okay, hidden layer can be so many layers, so that I am not considering. Generally, we have input layer, hidden layer, and output layer. So that is why your answer will be IH plus OH. IH will be 5000 and OH is 100. That means if it is just a neural network, your answer is 5100. But as it is a RNN, we have to do this HH also, because H is connected to H. So that is why it is a recurrent neural network. That is why we have this 2500 parameter added. That is why our answer is 7600. Shyam Sundar, if you include base, how many? Base means, acha, bias, not base, bias, right? Not base, bias. 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 If you consider bias, then how many number of in the this? Okay, let's consider bias also. So if I consider bias, this is I and this is H. Okay, this is H, this is again H, and this is O. Okay, this is the network. This is O, this is O. Now we have input H. How many number of parameter? That is 100 into 100 into 50, right? 100 into 50. So 100 into 50. Okay, but as we have in the hidden layer 50 number of 50 what is size 50. So how many number of biases? We will have 50 biases, right? So your it is 100 into 50 plus 50. So you have to add plus 50. So it will be 5050. 5050 in the input and hidden if we have bias. And second, if you have bias between H and H, again we will have 50. That means 50 additionally. So that means earlier we have 2500, so 2550. And at the, sorry, let me spare my handwriting. So let me write it well. So in the input and hidden layer, if we consider bias, then we will have 50 additional parameter, because 50 biases will be there. So it will be 50 into, this is 5, okay, 50 into 100 plus 50, that is IH. Okay, that will be IH 50. Okay, so that means 5050. Okay, and in between hidden and hidden, that is 50 into 50, 50 into 50 plus 50. Okay, 50 into 50 plus 50, that means 2550. Okay, and between hidden and output state we will have 50 into 2 plus 2. Okay, so that many number of biases. So how many number of biases? It is 5050, and it is 2550, and then you will have 102. Just sum it up and you will get the number of parameter including bias. So if we have bias, we have this 102 parameter extra. Okay, this is the thing. 102 parameter means 7702 will come if you have bias. Okay, this is this is the thing. So is it clear? Is it clear? Okay. So let's move on to the next question. Arrange the following sequence in order they performed by LSTM at time step t. Selectively write, selectively read, selectively write, selectively forget. So these are the four different: selectively read first, write second, forget third, write, read and forget, read, forget and write, forget, write and read. So any guesses for this? What is the sequence? A, that is read, write, forget. Okay, A, someone is telling A, and what else? Okay, A, yeah, guys are telling A, that is read, write and forget. Okay, why not write, read and forget, or read, forget and write? Okay, so this is the thing, this you have to keep in mind. In this LSTM we follow this sequence, that is first we selectively read from the previous state st minus 1, so read will come first definitely. Then what we do, we just forget, selectively forget to create the new state. Okay, st. So first we have st, then we have this st, right? And that is why we do this selectively forget, then and then we selectively write. Okay, selectively write to generate st from st. Okay, sorry, this is not st, this is the st tilde. Okay, st forget it, right? Yeah. First what we will do, first we will do the selectively read, then selectively forget and selectively write. Okay, so option C is the correct answer. This you need to remember. Okay, so this you need to remember. First you selectively read, then selectively forget and selectively write. Okay, this you just need to remember. Okay, I know this is confusing, but you just need to remember this. First it do the selectively read, selectively forget, and then it do the selectively write. This is a question, this you just need to remember it. Okay, so this is the thing. Now let's move on to the next question. We are given a RNN where max eigen value lambda of a weight matrix is 0.9. The activation function used in the RNN is logistic sigmoid. What can we see about delta s del s20 by del s1? Okay, very close to 0. Value of del is very high. Value of del is 3.5. Insufficient information to say anything. So any guesses for this? Yeah, so C. Any guesses for this? Okay, so let me just clear it. So how we write this del s20 by del s1? We will write by this. I have told you we will have this w dash and sigma dash st, right? This we know, this the maximum value of this will be 0.25, right? And this we have to do 0.25 19 number of times. Yeah, from 1 to 19. That means 19 number of times we have to do. And w dash as lambda is given for the weight matrix, that is 0.9. So that is 0.9 into this sigma dash st, that means maximum value. Let's take the maximum value, that maximum value can be 0.25, so 0.25 to the power 90. So this is very small. Okay, this is very small and this will be very close to 0, right? So option A is the correct answer. Okay, so this will come 0.225 to the power 19, and this is very extremely small, and this is very close to 0. So this question is the illustration of this vanishing gradient problem, because here what has been happening is just forget this w. If you will just consider this only, that means 19 times you will do the maximum of sigma, that can be 0.25, and your answer will be very very small, that is very close to 0. So this is a practical illustration of your vanishing gradient problem. Okay, so option A is the correct answer. So is it clear to all of you? Okay. Now question number 8, which of the following is a limitation of traditional feed-forward network in handling sequential data? Option A, they can only process fixed length input sequences. Option B, they are highly optimizable using gradient descent methods. Option C, they can't model temporal dependencies between sequential data. Option D, all of this. Which of the following is a limitation of a traditional feed-forward network in handling sequential data? Any guesses? Yeah, D. All of this, they can't process fixed length input sequences. But this is true, right? They can only process fixed length. Yeah, this is a limitation. Yeah, they can only process fixed length. Yeah, yeah, this is a limitation. They are highly
Option
optimizable.
A.
Yeah, they are highly optimizable using the gradient descent method. Highly optimizable using the gradient descent method. That is true. Yeah, that is also true. They can't model. Yeah, this is completely true. They can model temporal data between. Yeah, this is true. This is true. This. What about option B? They are highly optimizable using the gradient descent methods. So we cannot say they are highly optimizable using the descent method. The gradient descent we are again using here also, right? We are using the same thing, back propagation. So that is why B, I don't think B is the limitation. Okay, they are highly optimizable. B is the you can say B is the good point, right? Not a limitation of a feed-forward neural network. Back propagation of over time, we have this limitation because we have this problem of vanishing as well as exploding gradient. So this B is the limitation of this RNN, not the traditional feed-forward network. A and C are the limitation of this traditional feed-forward network. So A as well as C is the correct answer. Okay. Yeah, this thing is actually an advantage. Okay, not a limitation. Here we have this limitation because we are doing back propagation over time and we have to multiply many data, and we have this problem of this thing, that is vanishing gradient problem, or this exploding gradient problem. So that is why option A as well as option C is the correct answer. Option B is actually the advantage of this traditional feed forward network over this RNN. Okay, so option A as well as option C is the correct answer. So is it clear? Okay. Which of the following is a formula for computing output of an LSTM cell? This is OT. This is the formula of the gate, output gate. This is the formula of the forget gate. This is the formula of the cell state. Okay, cell state using the forget gate only. Yeah, and this is the HT. Okay, HT OT into tan state. Okay, cell state. Cell state is nothing but the HT only. HT written in the form of forget gate. So which of the following do you think is the correct answer? A. Okay, here it has been asked which of the following computing the output. Okay, not the output gate. This is the formula of the output gate, not the output. Okay, so this is the thing. Okay, so OT is the formula of the output gate, but it alone does not compute the final LSTM problem. This FT is the formula of the forget gate equation, which determine how much the previous cell state is retained. This CT is the equation of the cell state update using the forget gate. Okay, and the new forget gate. Yeah, using the forget gate. This is the cell state update equation defining the new cell state with the help of this forget gate. And we have this HT. HT is the hidden state or the final output of the LSTM cell. Okay, so HT is the final output of the this LSTM cell. Okay, so here it has been asked which of the following is the formula for computing the output of the LSTM cell. So this HT or the hidden state, whenever you will do the output gate with the cell state, new cell state, you will get the output of the LSTM. So option D is the correct answer. Okay, option D is the correct answer. This is the formula of output gate, not the output state. Okay, you have to understand this. there are 3 gate, there are 3 state. Okay, here it has been out what is the formula of the output state. Okay, not the output gate. So this is the thing, the formula of the output state is this, option D. Okay, this is the thing. So is it clear? You just have to remember this thing about LSTM. I know LSTM is a big topic, but still you have to remember this thing. Okay, now which of the following is true about LSTM and GRU network? LSTM networks have more gates than GRU network. GRU network have more gates than LSTM network. LSTM and GRU have the same number of gate. Both LSTM and GRU network have no gates. Again, a very simple question. This, if you have read the theory or you have whatever I have discussed, you would remember. LSTM has 3 gate, 3 state, right? And this GRU has 2 gate and 2 state, right? This GRU does not have this forget gate. Okay, in the input gate we are accommodating the forget gate in this GRU. Okay, so GRU has 2 gate 2 state, LSTM has 3 gate 3 state. So LSTM has more number of gate than GRU. Okay, so option A is the correct answer. Okay, option A is the correct answer. Okay, you can refer to this formula. Okay, which is the formula? Yeah, you can refer to this. LSTM has three gates and 3 state. This is the formulas of your GRU. GRU has 2 gate and 2 state. Why we have 2 gate? We are just removing the forget gate. We are not removing, we are actually accommodating the forget gate inside the input gate, and we are writing it as implicit input gate, and we have this 2 state. So GRU has less number of gates than LSTM, or LSTM has more number of gates than GRU. So option A is the correct answer. Yeah, option A is the correct answer. Okay, so this is the thing. So is it clear to all of you? Okay, let me show about this. So so just I have kept this course for you all. I have kept this 2-3 course for you all. Recurrent neural network, it is a problem. Okay, how we can just formulate a problem of recurrent neural network by the Python. This you can just see. Okay, this I have given as an example problem. This is the problem. Okay, this is the problem. We have this given sequence of input over 3 time step x1 we have this input, x2 we have this input, and x3 we have this input, and we have this initial hidden state h0 is 0.1. Okay, the RNN parameters are input to hidden state wxh, that means the weight from input to hidden, that is 0.9, and the weight from hidden to hidden, that is 0.5, and yeah, just this has been given, and bias has been given 0.3. Activation function, it has been given, that is tan hx function. What is our objective? Our objective is to compute the hidden state at each time step. That means what is the s1, s2, s3, like that. And second, verify the solution using the Python implementation. So let's solve using manual solution. So manually, how you can solve? This is the tan hx function that we will implement after calculating the thing in the bracket. So okay, so what will be the thing in the bracket? That will be wxh, that means the weight. Wxh is the weight from input to hidden. Okay, input to hidden, and in the input. Okay, so that means if I just talk about h1, that will be equal to wxh into x1 plus whh into h0. Okay, h0 is given, that is 0.1 has been given. So just 0.9 into 0.7, 0.5 into 0.1, and we have this bias. Okay, bias is given 0.3. So just you can calculate this h1, that is coming approx 0.753. Similarly, you can calculate h2. H2 will be what? H2 will be this wxh into x2 plus this whh into h1. Okay, h1 is coming 0.753, so 0.5 into 0.753 plus this 0.3. Okay, and whatever the tan of it, because function you have to, function is the tan x is the activation function you have to just implement the function, and this will be your h2. Similarly you can calculate the h3. Similarly I have also tried with the Python, same answers are coming. You can just see, just I have just implemented the formulas in the Python and the same thing is coming. Okay, so this is the problem of the, this is one of the problem. Okay, someone is joining. Okay, okay, yeah, so this is where I was, yeah, this is one of the problem of the problem to find how to find the hidden state of a RNN. Okay, so this is the problem. Again I am repeating, we have this 3 input, we have this hidden state, and what we are interested to find, we are interested to find the hidden state. Okay, compute the hidden state at each time step manually, that we are interested. How we can find? We can find by this formula, that is h1 will be equal to the weight from input to hidden into the input plus the weight of hidden to hidden into the previous hidden state, and plus the bias, and function of the activation function of whatever in the bracket. Okay, an activation function has been given, we have to apply this tan hs function. So just calculate the h1, h2 and h3. Okay, so is this thing clear to all of you? Is this thing clear? Okay, nice. So that is how you can solve the problem of this RNN. Okay, how to find the hidden state. Similarly, you can find the output. Output is very simple. If the weight from hidden to output is given, that is WHO is given, just multiply the WHO with this hidden. Okay, with this hidden state, and add the bias, and then what you do, you just apply the activation function of the output layer. Okay, that will be cross entropy, or sorry, softmax or any other function. Just apply the function and you will be getting the output at time step 1. Similarly you can find the output at time step 2, and similarly you can find that output at time step 3. Okay, so is this thing clear? Okay, nice. So this is the thing. Similarly I have given the code for this RNN for stock prediction. Okay, RNN for stock prediction, you can, okay, this code is, okay, so this is the code. You can just see the code, you can see this. We have to again train the RNN. I have trained it for 50 number of epochs. Okay, just this, see these things, and this is the output coming. Yeah, it is not coming exactly, but yeah, we have some errors, but yeah, you can see the patterns are very similar, right? Yeah, there is some bias over here and there, but patterns are very similar. Okay, you can see this pattern and this pattern. This is the actual. Okay, this dotted one is the actual, and this is the predicted. So predicted. So yeah, we have something about the biases, but see, the pattern is coming very much similar to that. So that is how you can code RNN. Similarly, you can see the code for this LSTM and GRU also. Okay. We do not need to explicitly write everything. We can just call the Python from some library, LSTM or RNN or GRU, and we can implement the your input data to the RNN, LSTM or GRU, and you can get the output. Okay, you can also train it first and then you can get the output. Okay, so this is the thing. Okay, so by this I am ending the session for today. Okay, we will meet on the Tuesday. Next class will be on Tuesday, and then I will take a extra session. That will be a revision session that I will take on Friday, next Friday, and by that we will be completing my part of the TA. Okay, or you can say the course. Some other TAs would I might left with 1 or 2 classes more, but for my course, my content, I will take week 12 on this Tuesday, on coming Tuesday, and week. Okay, someone is joining now. And week and extra session I will take on the next Friday. Okay, so by this I am ending the session. Bye.